Okay, welcome to this equation on the forms of the equation of lines. Let's look at this equation right here. X plus 3y equals 6. Here's a graph of that equation. I know that this equation is the graph because I can plug various points that are on the equation in and it'll make the equation true. For example, here's a point that's on this curve, right? This point is 6 for x and 0 for y. And if I plug those values in, for x and y, it should make the equation true if this really is an equation of the line. Let's see if that's true. If I plug 6 in for x and 0 in for y, I get 6 plus 0 equals 6, 6 equals 6. So yeah, that point is on the line. That one checks out, right? I could pick another point. How about this one over here? This is the point -3, +3. Right, so let's try that one. If I plug that one in, let me use a different color here. X plus 3y equals 6. If I plug -3 in for x and 3 for y, what would I have? -3 plus 9 equals 6. Sure enough, that one works too. And in fact, I could plug all these different, any point that I could pick, including the ones that have fractional values, and that equation would be true because it is an equation that represents all the points on the line. Okay? That's a particularly nice form if I'm trying to graph by intercepts, right? Because I could use the cover-up method. I could say cover up the y term, and x is 6 tells me that the y-intercept here is 6 comma 0, or sorry, the x-intercept is 6 comma 0. And if I cover up the x, 3y equals 6 means y equals 2. So 0, 2 is the y-intercept. So this particular form of the equation is really nice if I'm trying to graph this using the intercepts method. Okay? But what if I perform an arithmetic operation to both sides of the equation, right? Would you agree that if I did this, x plus 3y, what if I added 4 to both sides? That's still the same equation, right? X plus 3y plus 4 equals 10. It's still the same equation. In fact, if I were to plug various points in, that would still be true. Okay? So I can basically do any operation, and I would get an equivalent equation. Because if I do the same thing to both sides, right, I would get another equation that's also a representation. So this equation would also represent that curve. Let's do another one. What if I had x plus 3y equals 6, and I decided to multiply both sides by 3? I could certainly do that too, and that would stay balanced. I'd have 3x plus 9y equals 18, and that would be another equation that also is going to make all those same points true. So those are two other equations. So all three of these equations, even though they look different, they all are basically the same equation because they're just found by doing algebraic operations on the original equation. So all of those could be equations of this line, right? All right. So when we say write an equation representing this line, as long as all the points on the graph make the equation true, the equation's correct. So there's many different equations. There's actually an infinite number of equations that can be written that represent that line. Here's just 3 of them right here. They were found by doing various kinds of manipulation on that first equation. All right. So it turns out, though, that there are some standardized ways to write the equation of a line. There's actually 4 ways, and so I'm going to talk about those 4 standardized ways. They're called the forms of the equation, and then we'll talk about how to convert back and forth between them. So there's 4 ways. They're called standard form, general form, slope-intercept form, and point-slope form. So I'm going to talk about all of them in this video. Okay, standard form is like this example down here, x plus 3y equals 6, right? For an equation to be in standard form, you have to have a term for x's, a term for y's on the left-hand side, and then a term for numbers on the right-hand side. All of the multipliers, the thing multiplying the x, the thing multiplying the y, and the number by itself, all of them must be integers, right? So a, b, and c are just placeholders for any numbers for integers, right? And then the other restraint is that the first one, the x term, must be positive. So you couldn't have negative x minus 3y equals -6. You would have to multiply everything by -1 to force that leading thing to be a positive for it to be considered to be in standard form. But standard form equations have an x term and a y term on the left side and a number term on the right side. Okay, that's called standard form. Ax plus by equals c is the general form of that. Okay, now there is something called the general form. It's almost like standard form. It's ax plus by minus c equals 0. So it's almost the same. The only difference is that there must be a 0 on the right side. So if you have an equation in standard form, that's this equation down here. Sometimes STD is used to abbreviate that, but let me write it out. Standard form. This equation's in standard form. If I wanted to force it to be in general form, all I have to do is subtract that 6 from both sides to make it x plus 3y minus 6 equals 0, and now it's in general form. Okay, so you can use algebraic manipulation to force a standard form equation to be in general form, or the other way around. Okay, so standard form and general form both have kind of x term, y term number. All right. The one that we're probably most familiar with from Algebra 1, 2 is the slope-intercept form, where we can directly read the slope and the intercept. Remember, that's general form is y equals mx plus b, where m is the slope, the number multiplying the x is the slope, and the other number is the y-coordinate of the y-intercept. Now, if you have an equation in, say, standard form, you can force it to be in slope-intercept form by doing algebra, right? We want only the y term on the left, so that means if we had, say, x plus 3y equals 6, we could subtract x from both sides, and we would be left with 3y equals negative x plus 6. And then you need to get just y by itself, so then you would divide everything by 3 to get y equals negative 1/3 x plus 2. That would be the same equation, but in slope-intercept form. So you could convert by solving for y, essentially. Same equation, same line. Okay, and then the last form is not used very often in Algebra 1, 2, but it's used quite a bit in the later math classes because it's extremely useful. It's called the point-slope form. This one requires a little bit of explanation. The y and the x are the variables, just like they always are. But this and the m is the slope, just like it is in the other equations. But this right here, the y0, x0, x0, y0 is just a point, and it can be any point on the line. So x0, y0 just means the x-coordinate and the y-coordinate of any point on the line. Let me give you an example. Let's say that I wanted to write a point-slope form equation for this line right here. Okay, well, first of all, I need to know the slope, so I would maybe pick a couple points here and say this goes down 1 for every 3 that it goes over, so I know the slope is negative 1/3, right? But then what I'd do is I'd pick any point. Let's pick this one, 3, 1, and then I make the 3 the x0 and the 1 the y0, and that means that when I write this, it would be, here's the general form, y minus y0 m x. Here's the template that I'm going to fill in, right? So I have the variable minus whatever y0 is, and in this case the y0 is a 1, and the slope is negative 1/3, the variable x minus the x-coordinate of that point, okay? And so I could use that red point there and the slope to write a point-slope form. So this is called point-slope because it uses any point on the line and the slope to write. The reason why this is nice is that you can just plug any point in. It doesn't have to be an intercept. It could be any point at all. And it also means that there are many correct answers because you can get a different answer depending on which point you picked, right? If I had picked, say, this point, which would be 0, 2, then the point-slope form equation would look like this. It would be y minus 2 equals negative 1/3 x minus 0, right? So you can get a different point-slope equation depending on what point you pick. And both of those are perfectly acceptable point-slope form equations for that line. Okay, so 4 forms. Standard form, general form, slope-intercept form, point-slope form. Okay, let's do a couple of these. Let's say I want to write a point-slope form equation, and then I want to convert to all the other forms. So let's do that. Well, we're going to need the slope, so let's find it. Let's see, this crosses there and there. Looks like I'm going down 2 for every 1 that I'm going over, so the slope of this line is negative 2 over 1, or negative 2. All right, and then let's just pick a point. How about I pick this point right here, 1, 2, as my x0, y0 point. All right, I'm going to write the point-slope form out. Y minus the y from the point I picked equals the slope times x minus the x from the point I picked. There it is. That's the point-slope form equation, or one of them. Okay, now to convert to these other things, I'm going to have to do some manipulations. So let me write what I know. I know the equation is this, but I want to convert it to slope-intercept form. So what would I do? Well, let's get rid of the parentheses first. Y minus 2 equals negative 2x plus 2. I have to multiply the negative 2 times the negative 1 there. And then I could add 2 to both sides to get y equals negative 2x plus 4. That would be the same equation, but converted to slope-intercept form. Okay, let's convert that to standard form. Now that I have this, y minus 2x plus 4, could I convert that to standard form? Well, standard form requires the x and the y to both be on the left side, so I'm just going to add a 2x to both sides. 2x plus y equals 4. Great, that's the standard form. And then if I want to convert to general form, I already know that 2x plus y equals 4 works. For general form, I have to have a 0 on the right side, so all I need to do is subtract a 4. 2x plus y minus 4 equals 0. Alright, so it was easiest to write the equation in point-slope form, and then I could convert using algebra to any of the other forms. Okay? Okay, here's another example, same thing. Pause the video, see if you can get this one complete, and then we'll move on. All right, let's find the slope first. There's a point, down 1 for every 2 that I go over, so the slope is going to be negative 1/2. Okay, and let's use this point right here. That would be 2, 2, right? 2, 2 is my x0, y0. All right, so what do I have here? I've got y minus 2 equals negative 1/2 x minus 2. That's a point-slope form equation. You could have other answers. Okay, let's use that. Let's get rid of the parentheses here. Negative 1/2 x. Negative 1/2 times negative 2 is positive 1. And then if I add 2 to both sides, I get y as negative 1/2 x plus 3. So that would be the slope-intercept form. Okay, standard form, y equals negative 1/2 x plus 3. Well, first of all, I have to add the 1/2 x to both sides to get the x and the y on the same side, but then I'm not allowed to leave this fraction here, so what I would do is multiply the entire equation by 2 to get x plus 2y equals 6. That's the standard form. And now that I know x plus 2y equals 6, I could just subtract 6 from both sides to get the general form. All right, so you could convert from any form to any other form. Point-slope form is particularly easy to get because you can plug any point in. Okay, let's just do a couple other things. Maybe it just says write this equation in slope-intercept form and standard form. Okay? Well, to do slope-intercept form, it looks like all I need to do is add 2 to both sides, right? Actually, we probably need to multiply out first. Let's get rid of parentheses. Negative 2/3 x minus 2/3. You know what? Let's get rid of the, no, let's keep going here. What if I were to add 2 to both sides here? Now I would get y equals negative 2/3 x. Then I have plus 2 minus 2/3. To do that, I would change the 2 into put this over 1, and then that way we can change it to a fraction. Let's see, if I want thirds here, that's the same as 6/3, right? 6/3 is the same as 2, getting a common denominator. So I can combine those. Y equals negative 2/3 x plus 4/3. That would be the slope-intercept form. Now, to convert to standard form, let me write where I'm at now. I have negative 2/3 x, let's see, plus 4/3. I would just go ahead and multiply the entire equation by 3 to get rid of those fractions. That'd be 3y. 3 times negative 2/3 is negative 2, and 3 times 4/3 is positive 4. And then I just need to add the x's to both sides to get them to move to the left. Okay, that would be standard form. All right. Looks like we're getting close to time. How many more examples do I have here? That's it. That's the last one. Okay. So, so let me just do a summary. Any equation which is true when you plug xy values in that are points on the line, if all those make the equation true, then that means that equation is the correct representation. There are many, many, many correct representations to represent a line. Okay? The 4 kind of agreed upon forms are standard form, ax plus by equals c, where a, b, and c are integers and a is positive. General form, same thing except that the c has been subtracted to the left. Right? Slope-intercept form, y equals mx plus b. and then point slope form y minus y0 equals m times x minus x0, where x0, y0 is any point on the line. And then you can use algebraic operations to convert between the forms. And just